Measurement and signature intelligence is a technical branch of intelligence gathering, which serves to detect, track, identify or describe the signatures of fixed or dynamic target sources. This often includes radar intelligence, acoustic intelligence, nuclear intelligence, and chemical and biological intelligence. MASINT may have aspects of intelligence analysis management, since certain aspects of MASINT, such as the analysis of electromagnetic radiation received by signals intelligence, are more of an analysis technique than a collection method. Some MASINT techniques require purpose-built sensors. MASINT was recognized by the United States Department of Defense as an intelligence discipline in 1986. MASINT is technically derived intelligence that, when collected, processed, and analyzed by dedicated MASINT systems, results in intelligence that detects and classifies targets, and identifies or describes signatures of fixed or dynamic target sources. In addition to MASINT, IMINT and HUMINT can subsequently be used to track or more precisely classify targets identified through the intelligence process. While traditional IMINT and SIGINT are not considered to be MASINT efforts, images and signals from other intelligence gathering processes can be further examined through the MASINT discipline, such as determining the depth of buried assets in imagery gathered through the IMINT process. William K. Moore described the discipline. MASINT looks at every intelligence indicator with new eyes and makes available new indicators as well. It measures and identifies battlespace entities via multiple means that are difficult to spoof, and it provides intelligence that confirms the more traditional sources, but is also robust enough to stand with spectrometry to differentiate between paint and foliage, or recognizing radar decoys because the signal lacks unintentional characteristics of the real radar system. At the same time, it can detect things that other senses cannot sense, or sometimes it can be the first sensor to recognize a potentially critical datum. It can be difficult to draw a line between tactical senses and strategic MASINT senses. Indeed, the same sensor may be used tactically or strategically. In a tactical role, a submarine might use acoustic sensors, active and passive sonar, to close in on a target or get away from a pursuer. Those same passive sonars may be used by a submarine, operating stealthily in a foreign harbor, to characterize the signature of a new submarine type. MASINT and technical intelligence can overlap. A good distinction is that a technical intelligence analyst often has possession of a piece of enemy equipment, such as an artillery round, which can be evaluated in a laboratory. MASINT, even MASINT, materials intelligence, has to infer things about an object that it can only sense remotely. MASINT electro-optical and radar sensors could determine the muzzle velocity of the shell. MASINT chemical and spectroscopic sensors could determine its propellant. The two disciplines are complementary. Consider that the technical intelligence analyst may not have the artillery piece to fire the round on a test range, while the MASINT analyst has multispectral recordings of it being used in the field. As with many intelligence disciplines, it can be a challenge to integrate the technologies into the active services, so they can be used by warfighters. Understanding, measurement, and signature. In the context of MASINT, measurement relates to the finite metric parameters of targets. Signature covers the distinctive features of phenomena, equipment, or objects as they are sensed by the collection instrument. The signature is used to recognize the phenomenon once its distinctive features are detected. MASINT measurements searches for differences from known norms, and characterizes the signatures of new phenomena. For example, the first time a new rocket fuel exhaust is measured, it would be a deviation from a norm. When the properties of that exhaust are measured, such as its thermal energy, spectral analysis of its light, etc., those properties become a new signature in the MASINT database. MASINT has been described as a non-literal discipline. It feeds on a target's unintended emissive byproducts, or trails, the spectral, chemical or RF emissions an object leaves behind. These trails form distinctive signatures, which can be exploited as reliable discriminators to characterize specific events or disclose hidden targets, while there are specialized MASINT senses. Much of the MASINT discipline involves analysis of information from other senses. For example, a sensor may provide information on a radar beam, collected as part of electronics intelligence gathering mission. Incidental characteristics recorded such as the spillover of the main beam, or the interference its transmitter produces would come under MASINT. MASINT specialists themselves struggle with providing simple explanations of their field. One attempt calls it the CSI of the intelligence community, in imitation of the television series CSI, Crime Scene Investigation. This emphasizes how MASINT depends on a great many sciences to interpret data. Another possible definition calls it astronomy except for the direction of view. The allusion here is to observational astronomy being a set of techniques that do remote sensing looking away from the Earth. Astronomers make observations in multiple electromagnetic spectra, ranging through radio waves, infrared, visible, and ultraviolet light, into the X-ray spectrum and beyond. They correlate these multispectral observations and create hybrid, often false color, images to give a visual representation of wavelength and energy. But much of their detailed information is more likely a graph of such things as intensity and wavelength versus viewing angle. National and multinational. There has been work on developing standardized MASINT terminology and architecture in NATO. Other work addresses the disappointments of non-cooperative target recognition. For this function, infrared beacons proved disappointing, but millimeter wave recognition shows more promise. Still, cooperative, network-based position exchange may be crucial in preventing fratricide. The bottom line is that MASINT cannot identify who is inside a tank or aircraft of interest. Numerous countries produce their own anti-submarine warfare sensors, such as hydrophones, active sonar, magnetic anomaly detectors, and other hydrographic sensors that are frequently considered too ordinary to be called MASINT. China is not reported to be pursuing the more specialized MASINT technologies, although it does produce its anti-submarine sensors. Germany following the first successful launch on December 19, 2006, about a year after the intended launch date. Further satellites were launched at roughly 6-month intervals, and the entire system of this 5-satellite Lupe synthetic aperture radar constellation achieved full operational readiness on the 22nd of July 2008. Italy and France are cooperating on the deployment of the dual-use Orfeo civilian and military satellite system. Orfeo is a dual-use Earth observation satellite network developed jointly between France and Italy. Italy is developing the Cosmos Skymed X-band polarimetric synthetic aperture radar to fly on 2 of the satellites. Russia does have non-imaging infrared satellites to detect missile launches. Russia produces, of course, a wide range of anti-submarine warfare sensors. United Kingdom UK developed the first successful acoustic system. sound ranging to detect hostile artillery and anti-submarine acoustic detection in World War I. In the 1990s, an improved acoustic system for artillery location, acoustic artillery location system, was introduced, which complements counter-battery radar. United States. Within the U.S. intelligence community, the Directorate of MASINT and Technical Collections Office of the Defense Intelligence Agency is the central agency for MASINT. This was formerly called the Central MASINT Office. For Education and Research, there is the Center for MASINT Studies and Research of the Air Force Institute of Technology. Clearly, the National Reconnaissance Office and National Security Agency work in collecting MASINT, especially with military components. Other intelligence community organizations also have a collection role and possibly an analytic role. In 1962, the Central Intelligence Agency, Deputy Directorate for Research, formally took on ELINT and COMINT responsibilities. The consolidation of the ELINT program was one of the major goals of the reorganization. It is responsible for research, development, testing, and production of ELINT and COMINT collection equipment for all agency operations. Technical operation and maintenance of CIA-deployed non-agent ELINT systems. Training and maintenance of agent ELINT equipment. Technical support to the third-party agreements. Data reduction of agency-collected ELINT signals. ELINT support, peculiar to the penetration problems associated with the agent's reconnaissance program under NRO. Maintain a quick reaction capability for ELINT and COMINT equipment. CIA's Office of Research and Development was formed to stimulate research and innovation testing leading to the exploitation of non-agent intelligence collection methods. All non-agent technical collection systems will be considered by this office, and those appropriate for field deployment will be so deployed. The Agency Missile Detection System project, deleted, based on backscatter radar is an example. This office will also provide integrated systems analysis of all possible collection methods against the Soviet anti-ballistic missile program is an example. It is not clear where ELINT would end and MASINT would begin for some of these projects, but the role of both is potentially present. MASINT, in any event, was not formalized as a U.S.-defined intelligence discipline until 1986. MASINT from clandestinely placed sensors. CIA took on a more distinct MASINT responsibility in 1987. The National Security Archive commented, in 1987, Deputy Director for Science and Technology Evan Hinneman established a new office for special projects, concerned not with satellites, but with in-placed sensors that could be placed in a fixed location to collect signals intelligence or measurement and signature intelligence about a specific target. Such sensors had been used to monitor Chinese missile tests, Soviet laser activity, military movements, and foreign nuclear programs. The office was established to bring together scientists from the DS&T's Office of SIGINT Operations, who designed such systems, with operators from the Directorate of Operations, who were responsible for transporting the devices to their clandestine locations and installing them. The National Geospatial Intelligence Agency, of course, plays a role in geophysical MASINT. Multinational counterproliferation. All nuclear testing, of any level, was forbidden under the Comprehensive Test Ban Treaty. But there is controversy over whether the Preparatory Commission for the Comprehensive Nuclear Test Ban Treaty Organization or the treaty organization itself will be able to detect sufficiently small events. It is possible to gain valuable data from a nuclear test that has an extremely low yield, useless as a weapon but sufficient to test weapons technology. CTBT does not recognize the threshold principle and assumes all tests are detectable. The CTBTO runs an international monitoring system of MASINT sensors for verification, which includes seismic, acoustic, and radionuclide techniques. See National Technical Means of Verification for a discussion of the controversies surrounding the ability of the IMS to detect nuclear tests. Military uses. Captains of warships, in the Age of Sail, used his eyes, and his ears, and sense of touch to measure the characteristics of wind and wave. He used a mental library of signatures to decide what tactical course to follow based on weather. Medieval fortification engineers would put their ear to the ground to obtain acoustic measurements of possible digging to undermine their walls. Acoustic and optical methods for locating hostile artillery go back to World War I, while these methods were replaced with radar for modern counter-battery fire. There is a resurgence of interest in acoustic gunfire locators against snipers and urban terrorists. Several warfighter application areas are listed below. Also see deeply buried structures. Non-cooperative target recognition MASINT could be of tactical use in non-cooperative target recognition, so that, even with the failure of identification friend or foe systems, friendly fire incidents could be prevented. Unattended ground senses. Another strong need where MASINT may help is with unattended ground senses. During the Vietnam War, UGS did not provide the functionality desired in the McNamara line and Operation Igloo White. They have improved considerably, but are still an additional capability for humans on the ground, not usually replacing people altogether. In the U.S., much of the Igloo White technology came from Sandia National Laboratories, which subsequently designed the Mini-Intrusion Detection System family, and the U.S. Marine Corps' GSQ-261 Tactical Remote Sensor System. Another major U.S. Army initiative was the Remotely Monitored Battlefield Sensor System, which it upgraded to improved REMBASS, and now is considering REMBASS-2. The REMBASS generations, for example, increasingly intertwine interconnections of infrared MASINT, magnetic MASINT, seismic MASINT, and acoustic MASINT. The UK and Australia are also interested in UGS. Thales Defence Communications, a division of French Thales and formerly Recol, builds the Covert Local Area Sensor System for intruder classification for use in 35 countries, including 12 NATO members. Australia adopted the Classic 2000 version, which, in turn, becomes part of the Australian Linux system, which also includes Textron Systems Terrain Commander Surveillance System. Classic has two kinds of sensors: optical acoustic SATCOM integrated sensor and air deliverable acoustic sensor, as well as television cameras, thermal images, and low-light cameras. ADAS sensors were in a U.S. program, Army Rapid Force Projection Initiative Advanced Concept Technology Demonstration, using OASIS acoustic sensors and central processing, but not the electro-optical component. ADAS sensors are placed in clusters of 3 or 4, for increased detection capability and for triangulation. Textron says that the ADAS acoustic sensors can track fixed-wing aircraft, helicopters, and UAVs as well as traditional ground threats. ACTD added Remote Miniature Weather Station from System Innovations. These RMWS measure temperature, humidity, wind direction and speed, visibility and barometric pressure, which can then be sent over commercial or military satellite links. Employing UGS is especially challenging in urban areas, where there is a great deal more background energy and a need to separate important measurements from them. Acoustic sensors will need to distinguish vehicles and aircraft from footsteps, and things such as construction blasting. They will need to discriminate among simultaneous targets. Infrared imaging, for the urban environment, will need smaller pixels. If either the targets or the sensor is moving, micro-electromechanical accelerometers will be needed. Research programs. Smart Dust and Wolfpack. Still more of an UGS research program, under DARPA, is Smart Dust, which is a program for developing massively parallel networks of hundreds or thousand motes, on the order of 1 cubic millimeter. Another DARPA program is Wolfpack, a ground-based electronic warfare system. Wolfpack is made up of a pack of wolves. Wolves are distributed electronic detection nodes with location and classification capability, which may use radio frequency MASINT techniques along with the LINT methods. The wolves could be hand, artillery, or airdrop delivered. Wolfpack may fit into an Air Force program for a new subdiscipline of counter-ESM, as well as distributed suppression of enemy air defenses, an enhancement on SAAD. If the wolves are collocated with jammers or other ECM, and they are very close to the target, they will not need much power to mask the signatures of friendly ground forces, in frequencies used for communications or local detection. DSEAD works in a similar way, but at radar frequencies. It may be interesting to compare this counter-ELINT discipline with ECCM disciplines. MASINT is made up of 6 major disciplines, but the disciplines overlap and intertwine. They interact with the more traditional intelligence disciplines of HUMINT, IMINT, and SIGINT, to be more confusing, while MASINT is highly technical and is called such. TECHINT is another discipline, dealing with such things as the analysis of captured equipment. An example of the interaction is imagery-defined MASINT. In IDM, a MASINT application would measure the image, pixel by pixel, and try to identify the physical materials, or types of energy, that are responsible for pixels or groups of pixels. Signatures. When the signatures are then correlated to precise geography, or details of an object, the combined information becomes something greater than the whole of its IMINT and MASINT parts. As with many branches of MASINT, specific techniques may overlap with the 6 major conceptual disciplines of MASINT defined by the Center for MASINT Studies and Research, which divides MASINT into electro-optical, nuclear, geophysical, radar, materials, and radio frequency disciplines. A different set of disciplines comes from DEA, nuclear, chemical, and biological features, emitted energy, reflected energy, mechanical sound, magnetic properties, motion, and material composition. The 2 sets are not mutually exclusive, and it is entirely possible that as this newly recognized discipline emerges, a new and more widely accepted set will evolve. For example, the DEA list considers vibration. In the Center for MASINT Studies and Research list, mechanical vibrations, of different sorts, can be measured by geophysical acoustic, electro-optical laser, or radar sensors.